All right, welcome back, everyone. We're going to get started on day 4 p.m. We're going to be getting into fundamentals. So just like this morning, we have one lesson, one lab, and one challenge, as well as our TLOs and ELOs. So let's quickly go over that. For TLOs, explain how text is converted to numbers through tokenization and embeddings. Build and train a simple language model that generates text. ELOs describe why subword tokenization is preferred over character or word tokenization. Use tick token to encode text into token IDs and decode IDs back to text. Explain how token IDs map to embedding vectors using NN embedding. Compare embedding dimensions across different models. Describe next token predictions as classification over a vocabulary. Explain how temperature affects the randomness of text generation. Describe the role of attention in connecting relevant tokens. And for the challenge, you guys will be building a bigram model using NN.embedding and NN.linear. And then train the language model using cross entropy loss and generate text autoregressively. So today is about understanding how the models you built connect to large language models like GPT and Claude. Now that you can train, evaluate, and deploy classifiers, you'll learn how text becomes numbers through tokenization, how embeddings capture meaning, and how LLMs predict the next token. The same concepts powering modern AI systems. What are we trying to accomplish? This afternoon, we aim to bridge our classifier knowledge to large language models. By the end of this lesson, you will understand how tokenization converts text to token IDs, how embedding layers map IDs to meaningful vectors, and how next token prediction works at scale. You'll experiment with a real tokenizer, build embedding layers in PyTorch, and create a simple bigram language model that actually generates text. Any questions before we get started with the lesson? Okay, let's go. So overview, large language models like GPT and Claude use the same fundamental concepts we learned this week, just at a massive scale. So today you'll understand how text becomes numbers through tokenization, how words are represented as vectors through embeddings, and how LLMs predict the next token. These concepts bridge your classifier knowledge to modern AI systems. So what's the core problem? Neural networks only understand numbers. Your classifiers took numeric input, so the pH levels, fruit weights, diameter, and produce numeric outputs, which were our probabilities. But language is text, so how do we convert words into numbers? The sentence, "I love coding," needs to become a tensor before any neural network can process it. And this goes for any text. So this conversion from text to numbers is the foundation of all language models. So let's take a look at the difference between our classifiers and the language models. So with our classifiers that we've been working on all week, we have inputs. So our inputs consisted of numerical values and it has a fixed size, and the output would be the probability. So for language models, on the other hand, we have text, but we need to convert it to numbers, and the variable length can be any size. So, and the output for that would be the next word probability. So it's really trying to figure out what token should come after it. Tokenization. Tokenization splits text into smaller pieces called tokens, then maps each token to a number. So why don't we just use characters? Well, there are three different approaches that are shown here. So we have characters, words, or subwords. If we break it up by characters, the vocabulary size would be around 100. So you got to take account of lowercase letters, uppercase letters, digits. So that's why it's so small. And that's the problem. It's too granular and it loses meaning. Now, if we break it up by words, it's going to be bigger. a lot bigger. So it's going to be at around 100,000 plus, and there's too many unique words. If we go with the subwords approach, uh, it's pretty much breaking it up uh, however it does it, but it's not just a single character or a single word. It actually uh, splits up words. Maybe, if you have running, it'll say run and then ning, or it'll have run with two N's and then ing at the end. So it just pretty much breaks it up, and uh, that's the better approach to use out of the three because it's kind of in between. It's not too granular and it's not too many. So modern LLMs use subword tokenization, breaking words into meaningful pieces. How does tokenization work? Common words stay whole and rare words get split into pieces. So the word the is common, so it stays whole. Uh, the word running is rarer than the, so it gets split up into run and then ning. So it's split into the root and the suffix. Same thing for tokenization. So we have token and then ization. So it's split into meaningful parts. And then ChatGPT is uh, more uncommon, so it gets split up further. So we have chat, G, and then PT. So another example is the word unhappiness might become un and then happiness, or unhap and then iness. The tokenizer learns which splits are most useful during training. Token IDs, each token maps to a unique integer ID. So if we have the text I love coding, the tokens would get split up. The text would get split up into tokens of I, love, and coding. And as you can see here too, it includes the spaces. And then it also has for each token, it gets assigned a token ID. So I got assigned to 40, love got assigned to 1842, and coding got assigned to 14,320. So usually the more it's not a rule, but the more common words are usually uh have lower ID numbers, and uh that's because tokens are learned in frequency order, so more frequent tokens are added earlier, and then token IDs are assigned in the order that tokens are added. But again, it's not like a rule. It's just kind of a convention. So the vocabulary is a fixed dictionary mapping tokens to IDs, and GPT-4 has around 100,000 tokens in its vocabulary. Tokenization in practice, different models use different tokenizers. So here we have 4 different models: GPT-4, Claude, BERT, and Llama. GPT-4 uses tick token BPE. So BPE stands for byte pair encoding, and it builds a vocabulary by repeatedly merging the most frequent adjacent byte or character pairs. So the example says the same sentence tokenizes differently across models. Hello world might be 2 tokens in one model and 3 in another. This is why you can't mix tokenizers between models. So embeddings, token IDs are just integers. They don't capture meaning. The word king is it. So it gives us an ID as well. Isn't mathematically related to queen just because of their IDs. Embeddings solve this by representing each token as a vector of numbers that capture semantic meaning. And you guys have already been learned about vector embeddings, so this should be just a little bit familiar. from ID to vector, each token ID maps to a learned vector. So the word I, which is a token ID of 40, gets assigned to this vector, and then ID 1842 to this vector. So we have two components here listed in the table. The token ID is just one integer, and then the purpose is for dictionary lookup. Embedding is for semantic representation, and also is it is a float. Why embeddings work? During training, the model learns embeddings where similar words have similar vectors. A couple of weeks ago, we saw this when we were going over vector embeddings. So king minus man plus woman is equal to queen. So gender relationship captured. Paris minus France plus Italy is Rome. So there's a capital city relationship. And then running minus run is equal to swimming minus swim. And there's a tense relationship between the two. Words that appear in similar contexts end up with similar embeddings. So cat and dog have similar vectors because they both appear in sentences like the blank sat on the couch or I fed my blank. Embedding dimensions, larger models use larger embeddings. So as we go up in the model, so GPT-2 has as you can see has smaller embedding dimensions and smaller total parameters, while GPT-4 has uh, a much larger uh, embedding dimension and larger total parameters. So our fruit classifier this morning used two input features, but LLMs use thousands of dimensions per token. The prediction task, oh shoot, I forgot to record. Am I recording? Yeah.
You're recording.
Okay. Uh, Next token prediction. Given a sequence of tokens, predict what comes next. So we have an input. The capital of France is the output. Will be a probability distribution overall. Would be around 100,000 tokens, and then top predictions would be Paris, the and A. So we have also our percentage on the side of the probability that it would be that word. So our classifier, we had two classes, apple and orange, and then we had one prediction per input and then a binary output. LLMs, on the other hand, have around 100,000 classes, all tokens, and there's one prediction per position and vocabulary size output. So instead of just having that, uh, I guess that prediction coming out all the way at the end is going through at each step. So it's really trying to figure out what the next token is. Autoregressive generation, LLMs generate text one token at a time by repeatedly predicting the next token. So step one, and then it'll predict capital. So then step two will be the capital. Now it'll try to think of what's next. So the capital of. Step three, the capital of will try to predict what's next. So it predicts France, and then it just keeps on going and continues until it's done. And we see that same sequence down here in the table. So the capital of France is, and it starts off with the. So when you chat with Claude, each word is the response and each word in the response is generated one at a time. The model sees everything so far, your message plus its partial response, and predicts the next token. temperature and sampling, the model outputs probabilities. How do we choose which token to use? So we have three methods listed over here. So greedy, that's when the temperature is at 0. So it's absolute. It's not really, it doesn't get creative. I kind of just think of it as being stubborn. So it's set on one that one choice it likes. So it's real deterministic and repetitive. It always picks the highest probability. We also have temperature over here. It scales probabilities before sampling. So the higher the probability, or the higher the temperature, the more random it is. So it gets more creative. Top P, it's a sample from top tokens, summing up to whatever you specify for the P. So say you specify like 97%, 97% or something, or 0.97, it'll take the top three or top however many probabilities that you have, and it will add those percentages and uh, make sure that it equals uh, to that whatever you set the P as. And this is the most balanced creativity. So we can kind of see that over here in this little example. So probabilities, we have Paris as 92%, London as 3%, Berlin as 2%, and the as 1%. So if we have a temperature of 0, it'll always be Paris. If we have a temperature of 0.7, usually it'll be Paris, but sometimes it can be London. And then a temperature of 1.5, there's more variety, but there's also occasional mistakes. Any questions on that? So now let's get to attention. How does a model know which words matter for predicting the next token? The problem is in the cat sat on the mat because it was tired. What does it refer to? The model needs to connect it back to cat, not mat. This is what attention solves. So attention measures how much one token uses other tokens to build its own meaning. So let's look at this conceptual attention mechanism. Attention lets each token look at all other tokens and decide which ones are relevant. So processing tired in the cat sat on the mat because it was tired. Uh, we have some attention weights listed below. So the is not relevant to tired, so that's why it has a much lower float, so it's 0.01. Cat is a higher float, so 0.35, because it's relevant because uh it's what is tired. Sat point is 0.15. It's somewhat relevant. I was thinking of it kind of like I mean, when you're tired, you'll sit down or lay down. On is not so relevant, so it has a score of 0.01. But I was also thinking, what if like you're laying down on a bed or on couch or something. But yeah, over here we have a low weight to it. The it's not relevant as well. Mat is slightly relevant because uh that's where the cat is laying down. That's kind of why I was thinking about how this could maybe be higher. The word on, because is not too relevant, it has a score of 0.02. And then it has a weight of 0.30. It's relevant because it refers to the cat. Was is somewhat relevant, and it's relevant because it carries grammatical structure that helps interpret who is tired and how tired is being asserted. So over here we have our tokens, cat, it, and then the on, as we just went over. cat and it have a high attention weight. And the interpretation is for cat is the subject being described. It is the pronoun reference. And then for the and on, it's a low attention weight because it's not relevant to the word tired. Self-attention, every token attends to every other token, including itself. So sequence length is 10 tokens. Attention matrix is 10 by 10 equals 100 attention weights. So this is computationally expensive. It's why LLMs have context length limits. So these kind of just multiply against itself to get that attention computations. Example, Cloud has a context window of around 200,000 tokens. That's 40 billion attention computations per layer. And there are many layers. This is why LLMs require so much compute. We also have multi-head attention. Instead of one attention pattern, models use multiple heads that each learn different relationships. So head one might learn subject verb agreement. Head two might learn pronoun references. Head three, adjective noun connections. Head four, long range dependencies. GPT-3 has 96 attention heads. Each head learns to focus on different linguistic patterns. And then we also have transformers. The transformer architecture combines everything. So we have our input text that gets converted to tokens. And then, so tokenization converts that text into token IDs. And then the token IDs is linked to embeddings. So IDs is linked to the vectors. And then we have our transformer block, which has self-attention, feed-forward network, and layer normalization. And it passes on to the output layer for vocabulary probabilities, which will determine the next token. So looking at this table, we have the four components: embedding, attention, feed-forward, output layer. So it's comparing it to the equivalent for our classifier. So embeddings is equivalent to input features, attention. It's not equivalent to anything because it's new. And then feed forward is equivalent to linear and ReLU. And then output layer is equivalent to the final linear layer. So scale comparison. So our fruit classifier this morning had 2 layers, 0 attention heads, and around 100 parameters. GPT-2 small has 12 layers, 12 attention heads, and then 117 million parameters. That's a big jump. And then GPT-3 has 96 layers, 96 attention heads, 175 billion parameters. GPT-4 has around 120 layers, around 128 attention heads, and then 1.7 trillion parameters. The architecture is similar. It's the scale that creates the capability. So connecting to our classifiers, the concept, we have input processing. So our models has numeric features, but on the other hand, LLMs have tokenization and embedding. We also have the concept of core computation. So our models have linear layers and activation, while LLMs, on the other hand, have those attentions and feed forward. Our output for our models have class probabilities. LLMs have token probabilities. For our training, we have BCE loss and the Adam algorithm. And LLMs have cross entropy and Adam variance. For inference, we have forward pass, and LLMs have autoregressive generation. So example, our water classifier does one forward pass to predict potable or not potable. An LLM does hundreds of forward passes to generate a paragraph, one pass per token generated. So a summary of what we just went over. We have 5 concepts: tokenization, embeddings, next token prediction, attention, and transformer. What does tokenization do? It takes text and gives it a token ID. Subwords balance vocabulary, size, and meaning. Embeddings take those token IDs and links it to a vector. So similar words have similar vectors. And then next token prediction has core training task. It predicts one tokens and repeats to generate. Attention connects relevant tokens. Each token looks at all the others. And then transformer is the full architecture. And key insight is embeddings, attention, and feed forward. So the fundamentals you learned this week: tensors, forward passes, loss functions, optimization are the same ones powering ChatGPT, Claude, and every other LLM. The difference is scale. So more parameters, more data, and more compute. Any questions? Okay, let's get into the lab. Let me move this to, let me bring this up to my other screen. All right. So our objective is getting hands-on experience with the core components of large language models. We'll be tokenizing text, building embedding layers, and see how next token prediction works, all using tools we already know. So let's go ahead and create our project directory. I'm just going to name it lab. And then I'm going to cd into that folder, create a file for our notebook. Going to open it up in VS Code. And then I'm also going to be creating a virtual environment. So let's do, I think, what is it? Then we'll go ahead and activate it. All right, we have our virtual environment set up. Now I'm also going to create a requirements.txt and just bring in the dependencies I have been using all week. And just go ahead and install that. Are there any questions so far? All right, let's upgrade our pip. Let's install tick token. go to our notebook, select our kernel, select our virtual environment, and let's create a new cell. Go ahead and put in our imports. Hopefully that pop-up didn't mess anything up. Go ahead and install our matplotlib. I don't know why I got a pop-up earlier that said I might have gotten some dependencies installed to the global scope when I was in my virtual environment. I think that's what's messing it up. Let me try something. Let me just go ahead and delete that directory and retry it again. We didn't get that pop-up this time, so hopefully it works. All right, sweet. All right, so we got our print statement. So we have the version of our PyTorch. Let's go ahead and continue. So in the next cell, we're just loading GPT Force Tokenizer. And so tick token again is OpenAI's tokenizer that turns text into numbers. And then CL100K base is the specific vocabulary or encoding used by GPT-4 and GPT 3.5 Turbo. So the print just tells us how many unique tokens the tokenizer can produce. So let's go take a look. So we can use 100,277 tokens. Continue to our next cell. So now we have the text hello world, and we're going to be converting this text into token IDs using that tokenizer that we specified up here. And we're just passing in the text. So we're going to print out the actual text, so hello world, the token IDs, and then the number of tokens. So as we can see, we have our text. Hello got converted to it got the token ID of 9,906, and then world got the token ID of 1,917 for a total of 2 tokens. So now we're creating a variable called decoded, and this is just taking that token ID and turning it back into that text. So let's see what we get outputted. So our original text was hello world, our decoded it's still hello world, and it does match each other, so that is true. Try in another new cell. So this time we have the text I love machine learning. So we're encoding that text using our tokenizer and then having some print statements. See what we get. So we print out our text, I love machine learning, and then we have token IDs associated with each token, or let's see how many, yeah, it actually tells us which words got turned into tokens. So we have I love and then machine learning, and then the exclamation point is actually a token on its own. And we have our IDs. And I guess maybe the exclamation point is more common, so that's why it has a ID of 0. Now we have a list of words. So we have the, which is very common, Python common, tokenization less common, ChatGPT, it's a uncommon, and then supercalifragilisticexpialidocious is very rare. So we have some more print statements. Let's see what we got outputted. So the just is one token by itself. So it's Python. Tokenization got split into two tokens. So we have token and then ization. ChatGPT got turned into three tokens. So chat, G, and then PT. And then this word got broke up to 11 tokens. Any questions so far? So again, this mainly looking at the commonality and how common that word is. Now let's get into, instead of words, let's get into sentences. So we have a list of sentences here. We have hi, hello, how are you? The quick brown fox jumps over the lazy dog. And then I'll try it out. Num Pneumonic, traumatic, scopic. Nah. Yeah, that word is a lung disease. And then we just have some print statements right after it. Let's see what we get. So hi is one token. Hello, how are you? Got split to 6. The quick brown fox jumps over the lazy dog. Got switched to 10. See how many words there are in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and maybe the period got its own token. And then, of course, this big word has 22 tokens in this sentence. In our next cell, we're creating an embedding layer. So we have two variables, vocab size and embedding dimensions. So vocab size, we have 10 possible tokens. And then for embedding dimensions, it's we have 4 dimensions. And then we're actually creating our embedding layer and throwing in our vocab size and embedding them into this right here. And nn.embedding is a PyTorch layer that maps token IDs to vectors. Right below them, we have our print statements. So we have our 10 tokens linked to our 4 dimensions. And then total parameters, you just multiply that 10 and the 4, you get 40. So let's go back to this embedding layer. So this will be, so it'll have 10 rows for each token, but then it'll have 4 dimensions within each of those rows. So that's why over here we're getting the embedding for token ID 3, so the third row. And then we're assigning that to the token ID. We're passing in that token ID to the embedding layer, which we will get our embedding. And then we have some more print statements. So token ID, we have 3, and then it got back our embedding, our tensor. So it has 4 dimensions, 1, 2, 3, and 4. And then we also have our shape. So torch size of 1 row with 4 dimensions, 4 columns. So now let's take a look at embedding multiple tokens at once. So we have a token sequence here. We have a tensor of 1, 4, 2, and 7. So the first row, fourth row, second row, and then seventh row. We're passing in that sequence to the embedding layer to get our embeddings. Let's see what we get outputted. So since we have 4 over here, again, these count for each token. So that's why we have 4 over here, and then there's 4 dimensions, which we will get 4 for this position. So it actually shows us our embeddings down here for each token for 1, 4, 2, and 7. And then this is just really showing how these embeddings are a matrix. So let's go ahead and run that. So here's our full embedding table. So we should have 10 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have 4 dimensions across. So here we have our linear layer. So uh, we have 4 and 2 is getting assigned to our linear variable. And we're just printing out the shape of it, the weight shape. And then same thing for our uh, embedding layer down here that we have 10 and 4. Let's see what we get output. So we have a linear layer weight shape of 2 and 4 for the top. And that's because so this is for the out features, and then this for the in feature because of how matrix multiplication works in PyTorch. Uh, while the embedding weights are the number of embeddings, and then the embedding dimensions. So over here, let's print it out. So for our for this print statement right here, it's just printing out what we specified for our vocabulary. So it's 50,257 tokens. Over here, we're specifying our dimensions, so 768. And then the parameters, again, you just multiply the vocabulary with the dimensions, and it'll get you 38,597,376. Over here on this line, so this is going back to our fruit classifier. So the 2 is the 2 input features. This 8 is for the 8 neurons. So that if you multiply those together, you'll get 16 weights. And then we have 8 uh, biases. So we add 8 to that 16, which we will get a 24. And then so that's for our first layer right here. And then now we're going to be getting into our second layer. Let me see if I actually have that open. So here's where that 2 came from, and then the 8. So that's our first layer. And then for the second layer, we're multiplying 8 by 1, and we're getting that from over here, from this linear layer, and we're adding a bias of 1. So if we do the math and do a PEMDAS order of operations, so we should get 33 parameters. So this right here was 24, and then this here is 9. So that's how we ended up getting these 33 parameters. And then now we're just looking at the difference between the two. So our GPT parameters and then our fruit classification parameters. So we just divide that from the GPT-2 and we get this number right here. So the GPT-2 embedding layer alone is 1,169,617 times larger. So over here we specify a variable named vocab size, set it to 100,000. We have our logits, so our scores for each possible token, and we're just doing setting that to torch random, and then passing in the vocab size. We're converting it to probabilities using the softmax, passing in the logits and then the dimension of 0. We have some print statements, and then we're finding the top predictions by setting our top K and then our top probability and top indices to equal this top K suffix to torch, and passing in probabilities and top K. And then we have another print statement. So as we see, our vocabulary size is 100,000. Sum of probabilities is 1. And then we get back our top 5 predictions. In this cell, we're applying temperature to control the randomness. So this function right here, apply temperature, it scales the logits by temperature before softmax. We have our original logits, some print statements. Let's see what we get back. So if the temperature is at 0.5, we have, for example, pears has a probability of 81.3%. If we increase it to 1, notice how pears has a decrease in its probability percentage. And the more we increase it, it just keeps decreasing. But notice how some of the other ones kind of increased just by a little bit. So again, that's because it's more creative. It has more to choose from, or it can choose from. Where is if it has lower temperature uh, pairs, prob Paris's percentage gets higher. So if we say if we had a zero, this Paris will probably be like 100%, 99%, something like that. Let's actually try it out. Yep. So now for this next cell, we're just taking a look at how LLMs generate one token at a time. So we have a simple vocabulary for demonstration. The cat sat on mat, dog ran, and then end. And then we have the length of the vocab for our vocab size variable. And then this is just a fake model that's simulating what a trained model might output. And we're getting into a function that generates text one token at a time with some print statements. See what we get back. So for step one, we start out with the cat had a probability of 40%. Use that. So now it's the cat sat. It was 60%. The cat sat on 90%. The cat sat on the 50%. And then the cat sat on the mat, which had a probability of 80%. So final output, the cat sat on the mat. And again, all these calculations are kind of happening in the background. It's going through this list and just trying to see which token would be best suited for the next to come right after that, whatever token we were on. So now we have a full pipeline. So step one, we tokenize. We have the text machine learning is. It gets tokenized. We embed it. We have an embedding dimension of 4. And then we process uh, the transformer layers, which we skipped over here. We just have a print statement. And then step 4, we have predict next token. So it's trying to see what is going to come after. And step 5, we just repeat it. See what we get. So this got tokenized to this right here. So we have 3 tokens. And then the shape is, so it's 3 tokens with 4 dimensions each. And then we're just trying to see which token, or yeah, which token will be next. We got back Mark. Trying to figure out where that came from. Let's see. Any guesses where this this came from?
I think so. Scroll up real quick, just to that. Yeah, so step four
Mm,
is just predicting the next token. It looks like for this, it's like a placeholder. I guess the first line output logits equals torch.rand in. I think it's just picking a random. Run it again. Can you run it again?
yeah, yeah,
This little section. I want to see if it comes up with something different besides mark. Yeah.
not yet.
So it looks like for the purposes of the exercise, it's picking a random token, not actually because we don't have that middle process with the attention and all that. And then it's taking that token, that random number that it generated, and pulling out of the, I guess, embeddings database or the total vocabulary, what word that would be, and
Mm,
sticking it there. And so it got mark last time. This time it got whatever it said.
yeah, Keaton.
Keaton,
Let's see. Let's run it one more time. See what we get back for that. Search.
parenthesis search. Yeah, it
Open
can't actually
parentheses.
do the logic behind it with
Mm,
the example. Especially, I think step three is where the magic happens, kind of, but we don't have step three
yeah.
because we don't have the ability to do attention or feed forward yet. I guess we could feed forward. I don't know. But yeah, it's just pulling a random one out of the total vocabulary.
Yep, yep. I agree with you.
But the idea was step three would provide that, and then you would feed that in, append it to the end, do it over and over and over until you build your full sentence or paragraph or whatever, just like the LLMs do.
Anybody have any questions? All right, let's compare it to our classifier. So we have our input, pre-processing, input to model, output one problem. Let's see what we get. Okay, yeah, these first ones are, I guess, the different sections or the different parameters to compare. Yeah, so I guess these are the parameters, and then the second index is for our classifier, and then the third one is for the LLMs. Nothing really too special on this, so it's just
Yeah, it's just rubbing in our faces
yeah,
how complicated the LLMs are versus what we did.
yeah. All right. And then yeah, that's the end of the lab. So are there any questions? I know I kind of went over it fast. So for the summary, the key parts to take away is tokenization, embeddings, next token, temperature, and autoregressive. So generating one token at a time and repeating. And tokenization is just getting those texts, converting it to token IDs, embeddings, linking those token IDs to actual vectors. And then uh, next token, I guess this kind of goes hand in hand with autoregressive, but this is just the actual step. And then this is for actually repeating it. And you can also modify the probability by messing around with the temperature of it. So key takeaways, tokenizer split text into subwords, common words stay whole, rare words get split. Embeddings are lookup tables, so each token ID maps to a learned vector. LLMs are classifiers with huge output spaces, predicting one of 100,000 tokens instead of one of two. And generation is iterative, so predict one token, add it to context, and then repeat. The concepts are the same as the classifiers, just at a massive scale. Any uh any questions? Let me stop recording.